In the previous lectures, we just looked at linear program rounding. And the idea is that we take a linear programming relaxation of our integer program, in this case of the vertex cover problem, and then we come up with a rounding scheme that designs x tildes around the optimal solution to this linear program. For the case of the vertex cover problem, if we saw an xv that's greater than or equal to 1/2, we set the rounded value to 1. And if xv is less than 1/2, we set the rounded value equal to 0. What's important to notice about this rounding scheme is that we did everything at once. That is, we took all of our linear program variables, and then we rounded them all with just some algorithm. There is a potentially other way called iterative rounding that doesn't round all the x's at once. That's what we're going to go through in this lecture. So in the iterative rounding algorithm, we're going to end up solving the linear program multiple times. And the idea is that whenever we solve the linear program, we might just get lucky. And some of the variables are already going to lie on our lattice. They'll be integer valued. However, some of them might not be integer valued, and the ones that aren't integer valued, we'll pick one, round it, and then resolve the linear program. So let's go through the iterative rounding procedure. First, we're going to start with some linear program optimal solution, x. And now, if some of the x's are non-integer, we're going to go through our rounding scheme. In our rounding scheme, we're first going to pick all the xi's that automatically were integer valued, that is, the linear program just happened to get them right, and we're going to fix them at xi tilde. So xi tilde is now going to be all of our integer valued variables. However, at least one of the variables in our linear program is going to be non-integer valued. And let's call it xj. We're going to take this xj and we're going to round it. And rounding here can be rounding with any algorithm. For example, in the vertex cover algorithm, we would take xj, the linear program solution, and if it was greater than 1/2, we would round up. And if it was less than 1/2, we would round down. The important point is that when we round xj, we have to stay feasible for our linear program and our integer program. Finally, after we've rounded this one particular non-integer value, we're going to resolve our linear program. When we resolve our linear program, we're going to come back. We may have all integer values, but if not, we go through the rounding procedure again. The idea here is that when we resolve our linear program, the xi tildes are all fixed. That is, once a variable turns into an integer, either by being part of the linear program solution or by us rounding it, it stays integer throughout the entire algorithm. We're going to go through the iterative rounding algorithm for a particular problem. We're going to choose an instance of the vertex cover problem. The graph that we input is pictured here. We have the vertices 1, 2, 3, and 4. When we write the linear program, we're going to minimize the sum of all the x's, the number of vertices that we pick, subject to every edge being covered. The edge 1, 2 has to be covered, the edge 2, 3 has to be covered, the edge 1, 3 has to be covered, and the edge 3, 4 has to be covered. After we solve this linear program solution, one of the optimal solutions is pictured here. We get a value of 1/2 for all of the vertices, or all the vertices. And before we go through with the iterative rounding algorithm, we should note that this is exactly the case where iterative rounding is useful. In this case, our linear program solution tells us almost nothing about what our solution should actually be. Everything is more or less homogeneous. Everything is 1/2. If we were to use our naive linear program rounding algorithm for this particular instance, we would get that we would pick every vertex, which is clearly not the right thing to do. So now let's continue with the iterative rounding algorithm. In this case, instead of rounding all of the variables, we'll pick one. We pick our variable xj. And in this case, we pick the vertex number 3. With our rounding scheme, we're going to take this value 1/2 and round it up to 1. And now we fix this value in our linear program solution. And by fixing the value, we say that x1 is equal to 1. We write in this additional constraint. Now that we fixed the value of this variable by writing this constraint, we solve the linear program again. When we solve the linear program again, we get a new solution, pictured here. Our new solution has an additional integer variable. The vertex 4 is now have the value of 0. So we get an integer solution or an integer variable for free by just solving the linear program. This is sort of the idea behind iterative rounding and why it should be better. But we still have some fractional values. So we'll take one of these fractional values, say vertex 2, set it equal to xj, and we're going to round it. In this case, we use the vertex cover rounding, so we round this value up. In this case, up to 1. And now we have a set of fixed values. And notice now that our fixed values include this newly rounded vertex, our previously rounded vertex, and also the vertex that we got for free from the linear program. The linear program just happened to spit out an integer value. So to fix these, we write the constraints for each one of them. We set x4 equal to 0 and x2 equal to 1. Now we have a new linear program and we solve it. In this case, the solution is pretty obvious. With all these constraints written, we fix the values of all but one vertex, so our final vertex in our linear program solution is going to get the value 0. In this case, there's no rounding left to do. All of our variables are an integer, so we now have our final solution, x tilde, with our fixed variables. This is how the iterative rounding procedure works. We fix one variable, round it, solve the linear program, and keep doing it until we finally get all of the variables equal to integers. This iterative rounding procedure is rather intelligent, and if you'll notice, in the previous procedure we ended up finding an optimal solution to our integer program. That's not always the case, and in particular, there could be one thing that's going to go wrong. While we choose some variable to round, that choice is in some sense very arbitrary. So for example, we could have solved our initial linear program here, gotten our linear program solution of all 1/2, and then we could have chosen, instead of vertex 3, vertex 4 to round. If we did this, then we would go through our iterative rounding algorithm, and after making the proper choices, we could end up with a final solution that looks like this. In this case, we've chosen vertices 1, 2, and 4 to cover all of the edges. This solution is not optimal, and in general, we're not going to find the optimal solution. But there's a particular point to notice here, which is during the iterative rounding algorithm, there was some arbitrary decision we made. We choose which variable to actually round. We can fix that a little bit. In this tweaked iterative rounding, we're going to use the same sort of idea, which is we're going to take a linear program solution, and we're going to continuously resolve the linear program, hoping in every step that we get some integer variables for free. So we're again going to start with a linear program solution, and then, as long as there's some fractional solution, we're going to fix all the integer variables, all the things that the linear program automatically set to an integer variable. And then for all the fractional variables, we're going to go through a little bit of a more in-depth procedure. We're going to take each one of these fractional guys, we're going to round it, and then we're going to solve the linear program solution. This is going to give us an objective value. When we do this for every fractional variable, we're going to end up with some linear program solutions, and some of them are going to be better than others. We're going to pick the xj to round in the final version that's going to give us the best linear program solution. In our vertex cover case, this would eliminate rounding the variable x4. After we've picked the best xj to round, we're going to round it, and then we're going to actually solve the linear program to actually come back to our step and go through the iterations again. So now we're solving the linear program many, many more times. For every fractional variable, we end up solving a linear program. This can potentially lead to better solutions, but at the cost of solving a linear program a lot of times. So although this tweaked iterative rounding technique seems like it's a really good idea, and potentially is, it can lead to a lot of extra computation and potentially for nothing at all.